Okay, so welcome to Math 119-312, the mathematics of pandemics. And so today is our last of the math reviews. So as a reminder, the exam is due this Friday unless you ask for an extension. Any excuse is acceptable for an extension, and I just need to get it before the end of exam period. You are allowed to stop the exam after you do the math part and pause, and stop the clock before you start doing the two essay questions. I will try to monitor the chat. It's going to be a little bit harder for me to see that based on how I'm presenting here. So please feel free to speak up. And then I thought we would just spend the time going over some of the math that we've done. So far the only question I've received has been to do Newton's method. If there are other things people want to see, please just send something to the chat or just speak up afterwards. And I will try to be watching the chat on my iPad while looking at the main computer so that hopefully I can see it that way as well. Okay. So the first thing we want to do is talk a little bit about Newton's method. So the question is, what is Newton's method? Why is it useful? And how do we actually implement it? So I'm just letting myself in on the iPad. Good, somebody let me in. Okay. So Newton's method is used to solve equations or to approximate solutions. So if I start off with a really nice equation, such as maybe 3x plus 5 equals 0, well, this isn't that bad to solve. We can just bring the 5 over to the other side, divide by 3, 3x equals -5, and from that we would then get x equals -5/3. So a linear equation is not going to be hard to solve at all. We could try something a little bit more elaborate, 3x squared plus 5x plus 7 equals 0. And that's a little bit harder, but using the method, completing the square, we can write a polynomial like this in the form ax minus h squared plus k equals 0. And you might remember this as vertex form of a parabola from many years ago. And from this, it's actually much easier to solve, and we can solve it very similar to what we did above. We would get ax minus h squared equals -k. Therefore, x minus h squared equals -k over a. X minus h equals plus or minus the square root of -k over a. So x is equal to h plus or minus the square root of -k over a. And you could of course solve it and just go back in terms of, well, what are h and k in terms of the coefficients of the parabola. It turns out, unfortunately, that we don't have a similar formula for degree 5 and higher, or for more involved equations. If we wanted to try to solve e to the x equals e, that's much harder to solve. And so we need a way to approximate solutions. One of the things that we're trying to do in this class is get a sense of what numbers really matter, get a sense of how to interpret things. One of the best descriptions I've ever heard of quantum mechanics from the great Richard Feynman was that some of the predictions are so accurate, it's equivalent to measuring the distance between Los Angeles and Boston to the thickness of a human hair. And at that point, the measurement is essentially close enough for all practical purposes for anything we need to do. So what Newton's method does versus divide and conquer is Newton's method uses calculus. It uses differentiability. Whereas divide and conquer just uses continuity. So it's not surprising that Newton's method can do a better job than divide and conquer because it uses more about the function. And the way it works is we have some function, y equals f of x, and we're trying to figure out, what is the value of x where the function vanishes. And we start off with some initial guess. So maybe we start off here is our point x naught, Over here would be the point x naught, f of x naught. And the slope here, the instantaneous rate of change would be f prime of x naught. And we draw the tangent line to the curve. And this is one of the main themes of calculus. It's not often spelled out in enough detail in high school as to, why are we spending so much time learning calculus? Why are we developing all these formulas? The idea is to take something that's very complicated and replace it with something that's simple and hopefully captures the key themes, the key items that really matter. And if you think about what's going on with viruses and modeling how a virus like COVID spreads to the world, we're doing the exact same thing there. There are so many things that are going on that we have to decide what really matters and what doesn't. So for instance, when you are trying to decide on the mathematical model you want to do for COVID, you might break people up into different groups. And the question is, well, what makes one person different from another? For COVID, should it matter which baseball team you root for? I don't think so. I don't think that is something that really matters. Could it matter where you live? Perhaps, maybe the virus has a greater impact in warmer climates or colder climates. It could matter on your gender. It could matter on your age. It could matter if you have pre-existing conditions. Left-handed versus right-handedness, does that matter? My gut feeling is no, unless left or right-handedness is maybe indicative of something else. But you want to try to figure out which are the key features that matter. If you try to understand everything, you're going to have a model that's so complicated, you will have trouble getting anything meaningful out of it. And it's very similar here in Newton's method, is we take a very complicated function and locally we approximate it by a straight line. The straight line is not going to be perfect. If it were, then our function would just be a straight line. The hope is that the straight line does a good enough job that if we are close to a root, it will help us get close enough to the root that a second approximation will then do a good job. And so now we look and see, where do we hit? We'll call that point x1. And then we play the same game again. Over here we'd have the point x1, f of x1. And we would have a slope f prime of x1. And then we draw the new tangent line to the curve there. And looking at this picture, you can see, wow, with 2 iterations, it's already pretty close. And again, this is not a proof, but it's hopefully giving you some idea of what's going on. And so we saw that when we did divide and conquer, every time we did an iteration of divide and conquer, we decreased our uncertainty by a factor of a half. So if you want to decrease by a significant amount, say get 3 more decimal digits, that's going to require 10 iterations of divide and conquer. For Newton's method, and there were some homework problems on this, it turns out that 1 iteration essentially doubles your decimal accuracy. So it converges a lot faster in many situations to the root than divide and conquer. So going through the mechanics of Newton's method, we have a sequence of points of guesses, x0, x1, x2, ... And the hope is that this converges to the root. It will not always converge to the root, but it often does. And so we need to figure out, how do we find the next one? So just drawing a little bit of what our function looks like. Here's our point. Here's the tangent line. And so we have the point, say, xn, f of xn. We have a slope, f prime of xn. Here's our point xn. And then here is our next guess, xn plus 1. So our next guess is where we hit the x-axis. So the first thing is we need to find the tangent line. And so this approximates the function. So we would get y minus f of xn equals f prime of xn times x minus xn. So this is one of the many different forms for the equation of a line. So we have lots of different ways to write the equation of a line. So the line through PQ with slope m is just y minus the y coordinate q equals the slope x minus the x coordinate. And so now, if we look at where this line hits the x-axis, hits the x-axis at the point xn plus 1, 0. And the y coordinate is 0 because we've hit the x-axis. So we get negative f of xn is f prime of xn, xn plus 1 minus xn. And it's xn plus 1 because that's our new point. And so now we can solve for xn plus 1. And if you look at this, it's very similar to what we did a few moments ago when we were trying to solve equations. We first bring the 5 over, then divide by the 3. We do very similar type analysis here. So we get negative f of xn divided by f prime of xn is xn plus 1 minus xn. So xn plus 1 is xn, bringing that over to the other side, minus f of xn over f prime of xn. And so now we have a very simple formula that gives us the next value in the sequence given the previous value. So if we know what f is at xn and we know its derivative at xn and we know the guess xn, we now have the next term in the sequence. So this is Newton's method. So all you have to do now is you have to figure out what is the value of your function at the point and what is the derivative at that point. Now, depending on what your function is, you can sometimes come up with a really nice formula so that you don't have to keep computing things again and again and again. So we know right now, for instance, xn plus 1 is xn minus f of xn over f prime of xn. So let's consider the example from class. Consider f of x is x squared minus 3, the roots being plus minus the square root of 3. Well, if we look at f of xn is just going to be xn squared minus 3, f prime of xn, so f prime of x is just 2x, is going to be 2xn. And so now we just do some algebra. And we get xn plus 1 is xn minus f of xn, so xn squared minus 3 over 2xn. So xn plus 1 is xn minus xn over 2 plus 3 over 2xn. So xn plus 1 is going to just be xn over 2 plus 3 over 2xn. I can pull out the 1/2, and I get xn plus 3 over xn. What's nice about this is I now have a really clear, explicit formula to calculate the next term in terms of the previous. I'm not always going to be so lucky to get this. And again, I don't need this. I could always just use the equation we have up here. But if you can do some algebraic simplification, then this is really nice and it's going to save you some time as you go further and further down. And so now that I have this, I can just use this to very quickly find the next terms in my sequence. And so if you wanted to use Microsoft Excel or Google Sheets, we would have a nice formula where each cell would be a function of the previous. So let me quickly go to Excel. Okay, so Newton's method for for x squared minus 3 equals 0. So here's the n, here's our xn, here's our f of xn, here's our f prime of xn, and then here would be our xn plus 1. So we start off maybe with, I guess, is 2. F of xn is going to just be equal to xn squared minus 3. The derivative is going to just be equal to 2 times xn. And then xn plus 1 was just going to be xn minus the function divided by the derivative. And now if we just fill down Control D, all I need to do is I need to change this cell over here to equal the cell over here. And now if I fill down like that, it will fix things up, and you can see how quickly it's going to converge. And so this is one way to do the problem. Another way we could do it is we could do here's n, here's xn, and then we could just use the formula we developed, here's xn plus 1. And so n is 0, we start off with 2, xn plus 1 would just be equal to 1/2 times xn plus 3 divided by. And we just fill down. I'll just change this one to be over here. And now when I fill down, we can see again how rapidly this is converging. Okay. Any questions on how we do this? Just go back to just post that in here. Okay. Any questions on Newton's method of divide and conquer? Okay, any questions on any of the other material we've done this semester? Okay, if there are no other questions, then I will wish you, oops, oh, we got one. Can we go over some of the probability? Okay, sure. So the question is, can you be a little bit more specific about what probability you want to go over? You have to be more specific. Which systems? Okay, so the question was like the Weibulls with extra variables. So let me just do like a real brief probability review. So we have some event A with probability P. Then the event not A happens with probability 1 minus p. So this is often called the law of complementary probability. If you know the probability of something happening, then you know the probability that it doesn't happen and vice versa. These are mutually exclusive events. You can't have A and not A happen at the same time. So a lot of times when we're trying to calculate probabilities of events, sometimes it is easier to calculate the probability that something doesn't happen than the probability that something does happen. And so in a lot of the models, when we're trying to calculate the probability something happens, you might want to try to calculate what is the probability that someone is infected. And so we have a different model, and sometimes we have a very simple thing, and we might say you have a probability P of being infected. And this is the simplest possible model. The probability is independent of who you are, and it's constant through all time. Maybe a better model is you have some model P that depends on time. Or more than just time, even better, depends on time and conditions. And so I've talked to some people who are doing mathematical modeling of COVID, and one of the things I suggested is that you could almost model it as if there are two viruses. There's the COVID virus and there's the education virus. And when the education virus hits you, it has a chance of changing your behavior. For example, it might make you wear a mask more, and it might make you socially distant, and it might make you do voluntary quarantines and cut down on things. And so all of a sudden, as you start engaging in those behaviors, we have seen in numerous presentations that these appear to have a significant impact on the spread of the virus. And so as you start to do these various behaviors, your probability of being infected can greatly change. And so when we're trying to model this, there's a lot of different things that can go on. On an exam, I am not going to give you a tremendously difficult problem to model or solve. We have world experts who've been working on this for almost a year, and they're still disputing questions about their models. Now, one of the things you can ask is, are your answers reasonable? If you start wearing a mask, socially distancing yourself, and voluntary quarantining, if your infection rates are going up, this is quite surprising. And it might make you, rethink some of the arguments, or maybe there's a math error somewhere. I remember in a thermodynamics textbook that I used as an undergraduate, there was a problem where you threw a cube of ice into a pool, and the question was, what happens? And the analysis in the book had a minus sign off, and it turned out that the heat went in the opposite direction as normal, and the whole pool froze because of the addition of an ice cube. Clearly, something is wrong in a situation like that. So over here, what's going on with the Weibulls is we're trying to find a way to model complicated behavior. So we want to model complicated behavior. Well, in some sense, it's not so hard to model, but we want to model in a useful way. And that's the key difference. It's one thing to have a model. It's another thing to have a model that you can do something about. So there was a great colloquium a few days ago about why there is no elementary antiderivative for the function e to the x squared. So when we're trying to do mathematical modeling, we need to deal with things, if we want a closed form solution, that are tractable. And that cuts down tremendously on what we can do. So if you're taking this as a 300 level class, you should have taken linear algebra, you should have taken multivariable calculus, you should have taken Calc 2, Calc 1. And one of the greatest lies in Calc 2, or at least misperceptions, is that you might leave the class thinking you can integrate. I can't integrate either. I have to do a lot of work to write down a function that has a nice closed form expression for the antiderivative of the integral. Most functions don't have nice expressions. We are fortunate that there's a large family or many families of functions that do have nice closed form antiderivatives, and these actually model a lot of things in the real world. So polynomials are good. Trig functions. Exponentials. Sometimes. Things like e to the x is okay, e to the x squared is not. And so what we want to do is we want to try to come up with a way to model something that we care about. And so the idea of a family is you want a family with parameters. And the more parameters you have, hopefully the more you can fit things to the real world. Now, a great concern is going to be how well do you need to know these values? Sometimes, if you need to know a value to 6 decimal digits of precision, we may not have that ability, and thus this may not be useful in anything we are trying to do. And so for the baseball game, we observed data that looked roughly like this, and this was, number of runs, scored, and this was the frequency. And so we could look and see how often was our team scoring so many runs. And if we could find a mathematically tractable function to model this, then we actually had the opportunity to get a closed form answer. And what's nice about a closed form answer is you can make inferences from it. Is once we get a formula, and the Pythagorean formula was runs scored squared over runs scored squared plus runs allowed squared, was approximately the winning percentage. And of course, 2 really should be, I think, about 1.7 something now, but it's often used as 2. What's nice about this is you could then make some inferences about, well, what would happen if you had an extra $10 million to spend? Would it be better for you to spend it on somebody who generates more runs for your team, or somebody who saves runs from being allowed? And there are formulas in the baseball community that allow you to estimate how valuable is a different player in the lineup or in the pitching rotation. And typically, about 10 runs scored equals another win in the season. So you have some rough idea, but this allows you to quantify and get a sense of how valuable is an addition going to be. It all comes down to, can we get closed form expressions? We want to do a double integral of the probability we score x times the probability we allow y, dy dx, and do it over the range y less than equal to x. So maybe x goes from 0 to infinity, y goes from 0 to x. Yes, this allows for a tie game, but because we're doing a double integral, the area of a tie game is essentially 0, so it doesn't matter. So it all comes down to, can we find a closed form expression? And so the simplest thing is, if we tried, p of x is a polynomial, or actually on the last page, I'll make this, p s for runs scored and pa for runs allowed. So if we have ps and pa are polynomials, we can do the integration very well. The problem is polynomials are absurd, because if you plot any polynomial, if the leading term is, say, c x to the n, if c is greater than 0, it's going to go up. If c is less than 0, it's going to go down and become negative. And so none of these are reasonable for long-term behaviors. So while we can do the integration that we want for this problem, if we use polynomials, there's no way we can actually model something like this, unless maybe we truncate. And maybe we say we only use these polynomials used for 0 less than equal to xy less than equal to, say, 20. It's absurd. it happens so rarely that a game has more than 20 runs, we will just truncate the polynomials like that. And so that is one approach, but to capture the shapes, we might have to have a polynomial of very high degree. And so what I noticed is, if I start off with some simple choices for the polynomials, I can actually do the modeling and I can get the exact answer. So I tried exponentials. PS, PA exponentials. E to the alpha x, e to the beta y. And in situations like that, I was able to do the integrals in closed form. And what was nice is I actually got the Pythagorean formula. Instead of an exponent of 2, I got an exponent of 1. And then once I knew that the exponentials worked, I said, well, let me see, can I generalize the exponentials? What if I tried a polynomial times an exponential? And from physics, I remembered some polynomials of the form v e to the minus alpha v squared. And I saw that if I tried that, I was able to get a closed form solution. And I actually got the exponent 2 that time. And then this is a really good moment where you stop and think, well, what do these have in common? What's the more general thing? And after a while, you might realize that what's going on here is that here the exponent is 2, and this is a 1. Here the exponent is a 1, and I can view this as an x to the 1 minus 1 or an x to the 0. So then I try, x to the gamma minus 1, e to the minus alpha x to the gamma. And it turns out that that is set up so that with a change of variable, it integrates very nicely. And then the rest is just, adding a little bit more flexibility. Is from this, you can go to x minus beta and just, shift where you start, gamma minus 1, e to the negative alpha, x minus beta to the gamma. But the whole point of trying to do this is I want something where at the end of the day, I'm not running a million or a billion simulations. I have something where I have a closed form answer. And then the last thing is, when you have a model like this, you always want to ask, is the answer reasonable? And so if I plot the Weibulls distribution, most of the Weibulls are going to look something like this. And you're going to have huge decay in the tail. So while it is possible for you to score 50 runs, you have a much better probability of winning the lottery every day for a year and being hit by a meteor every day as you leave. The probability becomes so small, it's just not worth worrying about. All right, does this answer the question? Okay, excellent. Interestingly, the chat shows up first on my laptop and then shows up just a little bit later on the iPad, which is also zooming in. Okay, any other questions? Okay, so the first question of homework number 3. So let me try to find that. Oh, so Zoom is just updating. I will definitely stay away from updating until we get to the end of the semester. Okay, so the first questions from homework number 3 is look at the final regular season standings in the American League. For each team, find the exponent C such that runs scored to the C over runs scored to the C plus runs allowed to the C equals the observed team's winning percentage. And so we have a interesting equation to solve. And then we do this for the final season standings in 2019. Which year do you expect is a better fit and why? And so we expect that the 2019 season will be a better fit than the 2020 season because the 2019 season had more games. And so let's say we observe, some team has W wins and L losses. And so I'm trying to see if I can switch the pen color. Okay, there we go. So we have W over W plus L should be runs scored to the C over runs scored to the C plus runs allowed to the C. So there's a couple of ways to solve this. The first is to think, what do we know? Well, we know the wins and we know the losses, and we know the average runs scored and the average runs allowed. So the only thing that we don't know is C. So we have one equation in one variable. Unfortunately, it's a nasty equation. And so the question is, how could we solve this? Well, we have two methods we could use. We could use divide and conquer. Or we could use Newton. There is another way, which was pointed out by someone in the class. We could actually do some algebra. If we pull out a run scored to the C from the numerator and the denominator, we get run scored to the C, run scored to the C, 1 over 1 plus runs allowed over run scored to the C. Well, run scored to the C over run scored to the C is just 1, so we get W over W plus L is 1 over 1 plus runs allowed over runs scored to the C. So doing a little bit of algebra, you get 1 plus runs allowed over runs scored to the C equals W plus L over W, which is just 1 plus L over W. So the ones cancel and you get runs allowed over runs scored to the C is equal to L over W. You could take logs and you would get C log runs allowed over runs scored equals the log of L over W. So C is the log of L over W divided by the log of RA over RS, assuming I haven't done any of the algebra wrong. So this is another nice example of the logarithm. We've seen that the logarithm can be used to make data nicer, to make it easier for us to see patterns in the data. Here's another way to use the logarithm to help us solve for this exponent C. So there is an algebraic solution for this problem, which is really nice. But if not, we could just do this with divide and conquer or Newton's method. And we talked earlier today about how to use Newton's method. Divide and conquer is very similar. The difference with divide and conquer is you use the left endpoint and the right endpoint. And so we could have a sequence of approximations to get closer and closer and closer to the correct value of C. All right, so that's the first question. The second question is, assume that the runs scored and allowed are discrete integer random variables. The model and class assume these are independent. Come up with a situation where you do not expect these to be independent and discuss what term you might add to the runs scored, runs allowed to account for the interaction. So interestingly, my son and I watched the movie Moneyball a few days ago. Great movie, great book. If anybody is interested in stuff like this, I've done a lot of guided work with Williams students on sabermetrics projects and consulting, and happy to chat with you. We have several Williams students who are in fact working in analytics now after working with me with many different major league franchises, and they keep emailing me about job opportunities and do we have any Williams students who might be interested. So if you are potentially interested in exploring something like this, please let me know. So there's a lot of different situations where you would not expect the ones scored and ones allowed to be independent. So in the beginning of a game, you're trying to score as many ones as you can. You've got a lot of game left to go. If you're in the bottom of the 9th inning and it's a tied game and you're batting, as soon as you score a run, the game is over. They often even stop the play. If you have your bases loaded and you hit a deep ball to the outfield and it's rolling around there, as soon as the runner from third crosses home and every runner makes it to the base that they need to get to, the game is over. And it doesn't matter what happens, the other ones are not allowed to score. So if you are in a situation where it's a tie game in the bottom of the 9th and you just need one run, if you have a runner on third and no outs, you will just try to hit a sacrifice fly and just score the runner. The other team will then change how they do their defense. Because all you need now is to score one more run, they will have their outfielders play shallow enough so that if they catch the ball, they can still throw the runner out at the plate. They will concede balls hit behind them that normally would have been outs, because if it's deep enough to score the run, it doesn't matter if the batter is out. And in fact, I have a thesis student right now who is looking at problems like this in terms of how you allocate your fielders. So this would be a situation where the runs scored and runs allowed are definitely not independent, because in a situation like this, as an offense, you would be willing to sacrifice scoring multiple runs to score just one run. You don't care about getting a 5-run inning. You don't care about not scoring as many as you could. You just want that one more run because that one more run is enough to win the game. Similarly for the defense, one of the things they might do, especially if your next hitter or two are good hitters, is they might intentionally walk them to load the bases and say, look, we really don't care about those batters because if the guy from third crosses the plate, the game is over. So let's walk these good hitters and hopefully we'll now be pitching against somebody who's a little bit weaker. We now have a chance maybe for a double play ball. And so these are situations where you would no longer have independence. So then the question becomes, how might you adjust your model to account for this? And there's a lot of ways you can do this. Notice I did not say, and then solve it. I just say adjust. So what you could do is you could have a different probability distribution for each game state. And so in terms of how many runs you score or allow, that could be a function of the game situation. Maybe for most of the game, it's the same as it would be normally. But in the 9th inning, in a situation like this, it's now a very different function to take into account the fact that the only thing that matters now is, do you score that additional run? And so your scoring frequency could change. So the easiest thing is to say that the probability function now has an inning dependence. Or even better, it depends not just on the inning, but on the score of the game. Related to this is if you have a huge lead, you will adjust how you choose your next pitcher. Similarly, if you're trailing by a lot, you will adjust who you have as your next pitcher. This was not a good year for Red Sox fans. One of the few bright spots is I was watching the Sox play the Yankees with my family, and the Yankees were being destroyed by the Red Sox. Now, it didn't really matter because the Yankees were going to go on to the playoffs and the Red Sox weren't, but the Yankees didn't want to lose any more of their relief pitchers and have them unavailable for the next game in a game that was already lost. So I think it was in the 8th inning with the Yankees down by 8 runs, they brought in their right fielder to pitch an inning. He gave up a run, but that was actually better on average than what the other pitchers were doing for the rest of the day. Normally, you would not bring in an outfielder to pitch, but their feeling was, look, the game is essentially over. We don't really think we're going to lose this. Let's conserve our resources for the next opportunity, for the next game. All right, does this answer the question? Okay. All right, so if you have any other questions before you start the exam, feel free to send me an email and I'm happy to find a time to just chat with people individually or in small groups. And then we will meet again on Wednesday. And again, I've tried to structure the end of the semester to give you maximum flexibility. I know in a general year, it's hard enough with all the different deadlines and all the different works from all the different classes. I have no idea what it's like now during COVID with all the different conditions everybody has. So the final is structured so you have far, far more time on it than you need. And this way you have the opportunity of choosing when you want to take it. So if you want, you can do just the math part first. That's half the exam. And then just stop, send that to me. I will grade that and give you a sense of how you're doing. And then you can move on and do the rest of the exam when you will. All right, have a good day all. Take care.